Let's try some infrared spectroscopy and mass spectrometry problems. These are practice problems based on chapter 14. So let's get cooking here. It says, which of the mass over charge values corresponds to the base peak in the following mass spectrum? Well, hopefully you remember the base peak. The base peak refers to the tallest, it is just the tallest peak in the spectrum. And so if we look at the possible answers, we have 45, 44, 29, 15. But you can see that the tallest peak is this one here, and the closest number to it is just below 30. So this must be 29. There's our base peak. The next question, question number 2, which mass over charge values correspond to the molecular ion? So now we're looking for the molecular ion, and we have 45, 44, 29, 15. Well, there's no way that you could have, something up here that comes from an M+1 peak or an M+2 peak. So if you were to assume that this was the molecular ion, you would be wrong, because if this is 29, if you do M+2 or M+1 or M+2, you'd only have something up here. And if you look at this peak, you can see it has a tiny little thing here, which is the M+1 that comes from the isotope. So this comes from carbon-13. So this comes from carbon-13, which is about 1% abundant, and therefore this would be our molecular ion, which has a mass of 44, and this is the M+1, which again comes from carbon-13. So now we've identified a molecular ion and we've identified a base peak. So again, the base peak is the tallest peak. The molecular ion is the mass of the parent, and in this case, we kind of solved it by process of elimination. Let's move on. It says calculate the HDI. For this formula, you have C14H14N2O. Remember that a nitrogen affects the HDI. It's like you're adding extra hydrogens, and an oxygen doesn't affect the HDI. So you could use the formula HDI is equal to 1/2 multiplied by 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, subtract X, like that. And when we do that, we plug our numbers into the formula. So we get 1/2 multiplied by 2 times the number of carbons, which is 14. So that's 28 plus 2, plus the number of nitrogens. There's 2 nitrogens. Subtract the number of hydrogens. There are 14 hydrogens. And then subtract the number of halogens. There are no halogens. So we have 28 plus 4. So that gives us 32. 32 minus 14 gives us 18. 18 minus a half, or multiplied by a half, gives us an HDI of 9. And so the answer is 9. For the next one, same thing. We want to use the same formula that I have in red at the top of the screen. So we have our HDI is going to be equal to 1/2 times the number of 2 times the number of carbons. So that's 2 times 9 plus 2 plus the number of nitrogens. That's 1. Subtract the number of hydrogens, which is 11. Subtract the number of halogens, and there's no halogens. And therefore, we end up with 1/2 multiplied by 10, which gives us 5. And so the answer is 5. Now remember, this formula is something that you want to have memorized for the quiz. So memorize this formula. And the good news is it will be handy for your entire duration of organic chemistry lecture and lab. That will not be in vain. Okay, which of the mass over charge values corresponds to the molecular ion for the following compound? So first, let's figure out what the formula is. We have 1, 2, 3, 4, 5, 6 carbons, so C6. There's no units of unsaturation, so 2N plus 2 gives us 14 hydrogens, and we have 1 oxygen. Remember, we deal with low resolution mass spectrometry in organic chemistry 1. So for the mass of the carbons, we have 6 times 12 plus 14 times 1 plus 1 times 16 for the mass of the oxygen. And when you tally all that up, you end up with 102. And so if we were to hit this molecule with a high energy beam of electrons. So we'll put here electrons, okay? High energy. We would make the radical cation, which would look something like this. We would knock one of the electrons off of the oxygen. Here's our molecular ion, and then it's going to have a mass over charge of 102. You know, just on the process of elimination, you could cancel, or you could say it's definitely not going to be E because E has an odd mass and there's no nitrogen in this molecule. Number 6, which of the following compounds would have an odd mass over charge value for the molecular ion? If you have an odd mass over charge, this means that you have an odd number of nitrogens in the compound. And if we look at these compounds, we have no nitrogens in here. We have an odd number of nitrogens in here. 1 is an odd number. Here we have an even number of nitrogens. In here we have no nitrogens. And so the answer must be 2. It's the only compound with an odd number of nitrogens. Next question, which of the following mass spectra shows the presence of bromine in a compound? Well, remember that bromine has 2 abundant isotopes. For bromine, we see the molecular ion, which comes from bromine 79, but then we also have an ion at N+2. So we have a molecular ion there that comes from bromine 81. And we know that the relative abundance of these, we'll put here the ratio is pretty close to 1:1. It's like 51 to 49, but 1:1 is close enough. And so if we zoom in on this mass spec here, this cannot be the compound because bromine has a mass of 79, and we have the highest mass peak having a mass of only 72, so that's impossible. If we go to the next one, we see something similar. We see something up here at 72, and so that cannot have a bromine in it. If we go up to the next one, oh, here we go. We see something that goes all the way up to 90, but we see that our highest mass looks like it's, you know, somewhere up around here. I don't know if, I can't tell if that's something or not, but there's nothing up here that would be heavy enough to have bromine in it. And there's also nothing up here that looks like it's got a 1:1 ratio of peaks. But if we go over to the first one, this is our base peak here, which is really huge, base peak, okay? But if you look over here, you see that we have 2 peaks that have roughly a 1:1 ratio in terms of their height. So this would be our molecular ion, and then this would be the M+2. It's the M+2 ion for our bromine. Now it's kind of hard to see what's going on here, but if you have 125, if this is 130, I can't even read this thing. So 131, 2, 3, 4, 5. So this looks like it's 136, kind of. Looks like that's what the mass over charge of the parent would be. Again, I can't really see that very well, but if you take 136 and you subtract 79 from it, you get 57. And if you zoom in here on the base peak, you see you have 51, 2, 3, 4, 5, 6, 7. And lo and behold, if you lose 79, so this is M minus 79, the loss of the bromine radical, you end up with this as your base peak, which makes sense. So loss of bromine. And so the answer, the only possibility here is the first one. There we go. Let's move on to question number 8. Which of the following compounds is consistent with the mass spectrum below? So we got a cool looking mass spec that looks good. Let's see what kind of compounds they gave us. We have an alkane. We have an alcohol. So this one is an alcohol. We have an ether. We have an amine. And we have none of these. Okay, so we have all these different functional groups. So what are some things that we could look for here? Well, the first thing we're going to do is we're going to look for the molecular ion. So we go 70, 71, 72, 73. Now, you can see that I kind of went in there with Photoshop or with, not Photoshop, but with Adobe, and I tried to make the molecular ion thicker. I didn't do the best job. It looks a little wacky. You can see I kind of added a little bit of detail over here. But the idea is that I wanted you to understand that the molecular ion has a mass over charge that's equal to 73. So if the molecular ion has a mass over charge that's 73, could anybody tell me which one of these compounds it must be? If the mass over charge is 73, there's only one possibility. If the mass over charge is 73, could anybody tell me which one of these it is? Yeah, thanks, Katie. Absolutely. We have an odd mass for our molecular ion. Therefore, the only possibility is the amine. Right? It's the only possibility because the amine has one nitrogen, and therefore it has an odd mass. If you draw the bond line structure of this compound, so it looks something like this. This is called diethylamine, which is neither here nor there. But what are some things that you could lose? You could lose the methyl radical. So if you had M minus 15, if you were to lose the methyl radical, then you take 73, subtract 15, and that would mean you should have something with a mass over charge, some kind of ion with a charge of 58. So you see that you have 60, 59, 58. So this is mass over charge equal to 58, and this is loss, or we could just put here M minus 15 from the loss of our methyl. What else could you lose? You could lose the whole ethyl, right? You could lose an ethyl, which is M minus 29. If we take 73 and we subtract 29, we get 44. Let's look at 44. We have 40, 41, 42, 43, 44. So this is M minus 29. So this is mass over charge is equal to 44. And again, that's from the loss of the ethyl. And again, you don't have to identify every single peak in the mass spec, but I'm just showing you how you might identify a couple of them. And we talked about loss of methyl and loss of ethyl. We also talked about alpha fragmentation or alpha cleavage, and this would be an alpha carbon, and this is your beta carbon. So if you were to break between this bond, that would also give you M minus 15, and that's, you know, the same peak that you see here. So this could either result from just the loss of the methyl radical or an alpha cleavage, which would produce the same radical. Anyhow, question number 9, I wouldn't ask you that one, so I'm just going to skip this one and say, FYI, I think I go over it on my YouTube channel, but again, I'll just leave that one for now. The next one, let's do another one of these, and then we'll take a look at some IR problems. The next one just says, which one of the following compounds is consistent with this mass spectrum? We go up here, we see our molecular ion. We have 70, 71, 72. So our molecular ion has a mass over charge of 72. And now we could look at these compounds that they've given us and see if any of them have a mass of 72. Well, I've gone ahead and calculated the masses of all of them. C5H12 has a mass of 72. So this is the right answer. If you go to the next one, it's C4H10O. That has a mass of 74. So that's not correct. The next one is C4H10O, which has a mass of 74. So that's not correct. And the last one, this has an odd mass. So odd mass, since it has one nitrogen in the molecule. And therefore, it cannot be the correct answer either. That would be impossible. If you take a look at A, if you just draw the compound out, so this would be 2-methylbutane, which looks something like 1, 2, 3, 4, 2-methylbutane. What are some things that we could lose here? We could lose this methyl to make a secondary carbocation. So let's say we did, you know, M minus 15. If you take 72 and you subtract 15, you end up with 57. And lo and behold, we have something with a mass over charge equal to 57, like that. And that's kind of the rationale that you want to take there. You could also lose all of this ethyl radical here. You could lose M minus 29, which would also produce a secondary carbocation. So 72 minus 29 gives you 43. And if you look here very carefully, we have 41, 41, 42, 43, which is this one here. And lo and behold, that this mass over charge is equal to 43. This happens to be the base peak. base peak. It's kind of interesting. So there we go. That makes sense. Let's move on from there. Let's try a couple of infrared spectroscopy problems. Let's see here. Let's try this one here, number 12. It just says deduce the structure of the compound. They give you a molecular formula. It's C3H3Cl. So if we have C3H3Cl, remember that a halogen can be treated like a hydrogen. And if we calculate the HDI for this, I've already gone ahead and done it. The HDI is equal to 2. So that means you could have, what, 2 double bonds, you could have a ring, and a double bond, you could have 2 rings, etc. Okay, so what do we see in our infrared spectrum? Well, I think the first thing that we might want to do is put the ruler at 3,000, and we'll look at the diagnostic region. So here's 3,000 reciprocal centimeters here. Let's draw a line and see what we have in above 1,500. So you could also draw a line at 1,500. So 1,500, so if this is 18, this would be 16, so that means, so 18. Oops, where's 1,500? So 1,500 would be here. There we go. All right. So what do we see? I mean, we see the ubiquitous kind of sp3 carbon-hydrogen stretching right here. So this isn't all that important. This is just sp3 hybridized carbon-hydrogen stretching. So that doesn't really help us a whole lot. But I noticed that we have something here, and we also have something huge here. And this is at about, if this is 3,200, this is 36. So this is 32, 33, 34, 35, 36. So this is at 3,300 reciprocal centimeters. So 3,300 reciprocal centimeters. And then I also see that I have something right here. So let me move my ruler over at this line right here. And if we see where that is, so we have 2,000, and this would be, so 2,000, 21, 22, 23, 24. So this is around 21, it's right around 2,200 reciprocal centimeters, close to it. And we'll put here 2,200 reciprocal centimeters. Well, if I go to my handout that I gave you, and you look for something that has an absorbance at 3,300, the only thing that you'll see is we have a sharp absorption at 3,300, and then we have for an alkyne, and then we have sharp stretching for a carbon-carbon triple bond. It says 2150 to 2,200, but this is very close to that. And so that tells me that I must have this in my molecule, right? This is sp hybridized carbon-hydrogen stretching, and this means that I've got a carbon-carbon triple bond. So if I put that together, it means I've got a carbon-carbon triple bond. That takes care of both of my HDI units, and then I must have this attached to it. So what's left over? I've got 1 carbon, 2 hydrogens, and a chlorine. So if I add 1 carbon to this, then what am I going to have on this? I'm going to have 2 hydrogens and a chlorine, and that must be the compound. That's the only possibility for this mass spectrum. There's no other possibility that it could be here. Any questions about that one? You know, sometimes students will find it tricky reading the scale, and you can see how the scale changes. If you go down here, you have 400, then you have 500, you have 600, 700 would be here, and then 800, but then it kind of gets smaller. It contracts between here and here, and then it contracts again up here. We squeeze it closer and closer together. And the reason why we do that is actually to make the spectrum a little bit easier to read, believe it or not. All right, let's try another one. What if we had this one here? You've got C7H8O. So C7H8O. They gave us the infrared spectrum, and they're asking us to deduce, excuse me, a possible structure. I've already gone ahead and calculated the HDI using the formula. The HDI is equal to 4 for this compound. And so that's a lot of units of unsaturation. Does anybody notice any functional groups that might be present in this compound? There's one that's, I'd say, the most recognizable on here. Yeah, definitely, right, Kiana? There's definitely an alcohol, isn't there? So we have the big old OH stretch. OH stretch. Now, another one that's we haven't gone over a ton, so I wanted to review it with you this morning, is an aromatic. If you have an aromatic ring, so an aromatic ring like this, the carbon-carbon double bond stretching that's aromatic, we usually see 2 to 3 signals or 2 to 3 absorbances. We'll just call them signals. Anywhere from 1600 to 1450 reciprocal centimeters. So if I look here and I zoom in, you see that this is 1400, this is 1500. So this is around 1450 here, and this is around 1600. So you see how I have these 3 absorbances here? This would be the aromatic carbon-carbon double bond stretching. So that means I have an aromatic ring in my compound. If we draw a line at 3000, so let's go over to 3000, which is, so if this is 32, this is 28, so this would be, sorry, Mr. Dion can't see, 29, 31, 32. Okay, so here's the line like this. So there's 3000. Well, you also see that you have some sp2 hybridized carbon-hydrogen stretching, which you would also see in an aromatic ring, right? We have all kinds of sp2 hybridized carbon-hydrogen stretching. So that means we've got an aromatic ring and we've got an alcohol on the compound. So we've got an aromatic ring and we've got an alcohol, but that doesn't take everything up, does it? We've only used up 6 carbons, so we've used up C6, and we've still got, so that means we've got another carbon. Well, where is that carbon going to be? It doesn't matter where you put it. You could put it anywhere on the ring. That's not important to me. But you notice that just below 3000, if you look here, we also have a little bit of, I'll write it in black, we have some sp3 hybridized carbon-hydrogen stretching. And so that would come from an alkyl group. So the only possibility is if we're only missing 1 carbon, it must be a CH3 group. Now you could put it anywhere you want on the ring. I don't care. You could put it here. You could put it here. That doesn't matter. That's not important to me. But this is a possible structure for this compound. And you could put that it could be this, or it could be this. It could be any one of these things. They would all be possible structures like that. Maybe I'll get rid of those and put all my double bonds in properly like that. Oops, like that. There we go. All right, so that's, a possible structure here. Let's try one more, and then we'll have to move on to the next chapter. But let's see here. Let's see if we can match the IR spectra to all of these different isomers. All of these compounds are C4H8O. So we have cyclobutanol, then we have this alcohol that's got a double bond in it. We have an aldehyde, we have an ether, and we have a ketone. Okay, I think the easiest thing to look for first would be the alcohol. So we have an alcohol here and an alcohol here. If you look at all 5 of these spectra, we see that 2 of them have OH stretches, this one and this one. So these are the 2 alcohols. Now, how are we going to differentiate between the 2? Stretch. How are we going to differentiate between these 2? Well, the cyclobutanol has no other functional groups. However, in this other compound, we have carbon-carbon double bond stretching. And then we also have, sp2 hybridized carbon-hydrogen bonds. And if we look at the first one, so if I put the ruler here around 3000, so let's do it here, and then we'll do it here. And I look at both of those, and what do you see? That just above that line, in the one in the bottom, you can see that you have a little something right here. And this is the sp2 hybridized carbon-hydrogen stretching, which is not present here. Furthermore, you can see a big absorbance here, in this one, and that comes from the carbon-carbon double bond stretching. If you go to the handout and you look at an alkene, we have weak carbon-carbon double bond stretching at around 1630 reciprocal centimeters. And therefore, this one would be the one that has two functional groups, the alkene and the alcohol. And then this one would be the cyclobutanol. Okay, so we've solved this one and this one. Is there any other ones that anybody was able to identify? Does anybody have an idea about any of the other ones? I noticed that two of them have carbonyls in them, right? If we're looking at the carbonyls, we have a carbonyl in the aldehyde and we have a carbonyl in the ketone. And remember that carbonyl stretching for an aldehyde or a ketone is going to be around 1700, so 1750 for a ketone and 1725 for an aldehyde. If we zoom in here, this is 15, 16, 17. So this is a carbonyl stretch. And then if we go over to this one over here, we have 15, 16, 17. So this is also a carbonyl stretch. So the question becomes, which one is the aldehyde and which one is the ketone? Well, again, if you go to that handout, it says that when we have an aldehyde, we also see stretches at 2750 and 2850. So let's take our ruler. We'll draw a line at 3000 reciprocal centimeters here. And then we'll draw a line at 3000 reciprocal centimeters here. What do we see? If you look at 2750, so this is 29, 28, 27. I don't see any kind of stretching here whatsoever. But if you go to this one, you have 29, 28, 27. And you can see that you have two stretches here. And those come from the aldehyde carbon-hydrogen stretch. That's these two here. We call this aldehydic carbon-hydrogen stretching. And therefore, this spectrum on the right represents the aldehyde. So this would be 2-methylpropanol. And the one on the left would represent 2-butanone, which is the ketone. That leaves us with only one other spectrum to be ethyl vinyl ether. I'll just move it down here. So that would be, there's our vinyl group. So here we go. And if you look at this spectrum, it makes sense. We have an ether and we have a vinyl group. We see that we have the carbon-carbon double bond stretching around a little bit above 1600. So this is the carbon-carbon double bond stretch. We also see that if we draw a line at 3000, let's draw a line at 3000, we see that we have the sp2 hybridized carbon-hydrogen stretching from these bonds here to these vinylic protons. And then for an ether, if you look at an ether, it says that we should have a carbon-oxygen stretch between 1300 and 1000. Here's 1000, here's 1300. The strongest signal that we see is this one here, and that would come from the carbon-oxygen stretch. And so this must be ethyl vinyl ether. And just like that, using the process of elimination, the handout, and our prowess in our knowledge of infrared spectroscopy, we were able to identify all of the spectra that match these 5 C4H8O isomers.